Boolean analysis is a beautiful blend of combinatorics, probability, and somewhat sneakingly, geometry. Oh, and the obvious analysis, of course. In this talk, we will see how a simple functional inequality, that is, an inequality which relates between one property of a function and another, can be strengthened in different ways. We will prove a conjecture by Talleyrand, as well as show stability results for functions which nearly saturate these inequalities. And while we won't be able to dive too deeply into the proofs, which employ martingales and Poisson processes and quadratic variation, I promise to show at least their sketches, in every sense of the word. And with that, let us begin. A Boolean function f is just a function on the n-dimensional hypercube -1, 1 to the n, which returns two possible values, -1 and 1. You can see the 4-dimensional hypercube on the right. This guy will follow us around for the rest of this talk. We can also think of a Boolean function as a partition of the hypercube into black and white vertices, and identify f with a set of white vertices itself. So this function represents a dictator function, which is 1 only if the first bit is 1, while this one is a parity function, which counts a parity of the input bits. Our two main players in this talk will be the following two properties, which are defined probabilistically. The first is the influence of a function in direction I. This is a probability that if you choose a point uniformly at random on the hypercube, f changes value when you flip the ith bit. So, for example, the influence of the first bit of the dictator function is 1, since the function always changes value when you flip the first bit, while the influence of any other bit is 0. The second main player is the variance of the function's value, when the input is a uniformly random point. Since f squared is always 1, we may also write it in this form. Although these properties are defined probabilistically, they have natural geometric interpretations. We'll start with the variance. Opening up the product, assume that the expectation of f is less than or equal to 0. We can always do this, since the variance of f is the same as the variance of minus f. The first term on the right-hand side is then just a number between 1 and 2, and the size of the variance is determined up to a constant by the expectation, that is, by the number of white vertices. The variance of f can then be seen as a measure of the volume of the set represented by f. The influence, on the other hand, measures the surface area of f. The ith influence counts the number of edges in direction I which connect black and white vertices, and the sum of all influences, also called the total influence, is a measure of the size of the edge boundary of f. Now, you know how mathematicians are. The moment they have two quantities, they have to try and compare them. And indeed, we can relate the variance and the total influence by the commonly called Poincaré inequality. You may have seen this inequality in other contexts. It holds for many function spaces, including functions on the sphere and functions in Gaussian space. When limited to the hypercube, it takes the following form. The variance is always smaller than the total influence. However, in this setting, it is actually quite weak. The variance of a Boolean function is always a number between 0 and 1, while the total influence can be as large as n, as demonstrated by the parity function. So the question is, can we do better than Poincaré's inequality for Boolean functions? And although I am just a pre-recorded voice, I can already see some of you in the audience nodding, and the answer is indeed yes. Perhaps the most famous strengthening is the KKL inequality, proved by Kahn, Calais, and Lineal in 1988. They showed that the variance is smaller than not just the total influence, but in fact it's smaller than the total influence divided by the log of 1 over the maximum influence. The KKL theorem already extends Poincaré's inequality to cases where the sum of influences tends to infinity with n, albeit slowly enough. This is a tremendous improvement, as many important functions have unbounded total influence. Perhaps the most famous example connected with KKL is the tribes function. To calculate this function, we divide the inputs into small tribes. The function gets the value 1 only if there exists a tribe all of whose members are 1. When the size of the tribe is chosen correctly, then the influence of every bit is of size roughly log n over n, whereas the function's variance tends to a constant as n goes to infinity. Thus, the KKL inequality is tight for tribes, as a quick calculation shows. However, the inequality is far from being tight for the majority function, which returns the most popular bit in the input. For this function, every influence is of order 1 over square root n, which is a wee bit too large for KKL. To deal with this function, we turn to a different strengthening of Poincaré, proved in 1993 by Michel Talleyrand. But first, we need to define the sensitivity of a function, a quantity similar to the influence. The sensitivity of a function f at point x is the number of neighbors of x on which f takes a different value. In other words, it is the number of edges in the edge boundary of f which emanate from x. Recall that the edge boundary is the number of edges between the white vertices and black vertices. We already saw that the total influence counts this quantity by going over all directions I from 1 to n. On the other hand, we can count this quantity by going over all vertices individually. Thus, the expected sensitivity is equal to the total influence. Poincaré's inequality can then be written as the variance of f is always smaller than the average sensitivity. Talleyrand showed that this can be considerably strengthened by replacing the sensitivity on the right-hand side with the square root of the sensitivity. We can think of this quantity as another measure for the surface area of f, though I'm afraid I don't have a geometric intuition for it. Talleyrand's inequality is tight for the majority function, but is not tight for tribes. In this sense, the surface area of Talleyrand and the surface area of KKL are incomparable. So we now have two different strengthenings of Poincaré's inequality. On the one hand, we have KKL, which is tight for tribes, but not for majority. And on the other hand, we have Talleyrand's inequality, which is tight for majority, but not for tribes. And although the two inequalities actually deal with different quantities, after all, the influences and square root of the sensitivities don't exactly compute the same things, it seems that there is some common ground to these two. So it is natural to ask then, if there is a single inequality which generalizes both of these, so both KKL and Talleyrand would just be special cases. In fact, Talleyrand conjectured that this is so, at least for functions with bounded variance. He conjectured that an extra factor involving the reciprocal of the squares of influences can be added on the left-hand side of his inequality. Although this expression may seem daunting at first, it is actually not all that unnatural. The sum of squares of influences is actually widespread in Boolean analysis. For example, it quantifies a function's noise sensitivity. This conjectured inequality is obviously an immediate generalization of Talleyrand's inequality on the right, since the left-hand side is now even larger. It can also be shown that if the variance is bounded below by a constant, then the KKL inequality follows from it as well. Let me show you the spirit of how that goes. Don't worry about following exactly the particular calculations too closely. With the assumption on the variance, we want to prove that the ratio between the sum of influences and the log of the reciprocal of the largest influence is greater than some constant. Starting with Talleyrand's conjecture, by convexity we can replace the right-hand side with the square root of the total influence. Squaring both sides, simplifying the log, and extracting out a factor of delta in the influence sum, we finally reach this inequality. We now have two cases. In the first case, the term that appears in the denominator in the log is smaller than the square root of delta. In this case, we can just plug in this delta into the log and obtain the desired inequality. In the second case, the product of delta and the sum of influences is larger than the square root of delta. But because log of 1 over delta is always smaller than 1 over the square root of delta, we again get what we want. Going back to our diamond of inequalities, we see that this conjecture indeed implies both Talleyrand's inequality and the KKL inequality. And we can happily say that with our paper, we can now turn the conjecture into a theorem. In fact, we were able to strengthen Talleyrand's conjecture in two separate ways. First, the inequality holds not only for square roots, but for various powers p. And second, we show that the quantity on the right-hand side can be made even smaller by multiplying it by a certain function which is always between 0 and 1. The expected value of the square of this function is bounded by the variance of f, and using the Cauchy-Schwarz inequality, this formulation of Talleyrand's conjecture can prove the KKL inequality even when the variance is not lower bounded by a constant. Before I say a couple of words on the stochastic techniques with which we proved this theorem, I should mention that in 1994, Talleyrand proved another strengthening of the KKL inequality, going in a different direction than his conjecture. Rather than dividing by the log of the reciprocal of the largest influence on the right-hand side, it is possible to divide by the reciprocal of the individual influences. We call this Talleyrand's influence inequality. In our paper, we reprove this inequality and also show a stability result concerning the surface area of functions saturating it. Up until now, we have only talked about the edge boundaries of functions. However, it's also possible to talk about the vertex boundaries. The inner vertex boundary is a set of all white vertices which are adjacent to a black vertex, and the outer vertex boundary is a set of all black vertices which are adjacent to a white vertex. The size of the vertex boundary can differ from that of the edge boundary by up to a factor of n. We showed that if Talleyrand's influence inequality is tight up to a constant multiplicative factor, then both the inner and the outer vertex boundary of the function is large, a constant proportion of its variance. This is a first small step towards understanding the form of functions which are close to saturating the inequality. In the remaining time, I'd like to talk about our proof methods. Eventually, all of the properties involved in Talleyrand's conjecture are the expectation of some quantity with respect to the uniform measure on the hypercube, the expected square root of the sensitivity, the variance, and even the total influence in the following way. Define the derivative in direction I at point x to be half the difference between f's value when xi is 1 and its value when xi is minus 1. This quantity can be either plus 1 or minus 1 if f's value changes, but is 0 if f of x doesn't change when flipping the ith bit. So the square of the derivative is 1 only when flipping the ith bit changes f's value. The total influence is then the expected sum of derivatives squared, or in other words, the expected squared magnitude of the gradient. So when calculating these quantities, there is always some underlying random variable which is distributed uniformly on the hypercube. The idea behind pathwise stochastic analysis is to generate this random variable in a clever way. For example, instead of generating all n bits at once, you can think of a discrete process where you start without any knowledge about your input and then reveal the bits of the uniform vector x one by one. At time I, you reveal bit xi and see what you can learn just from revealing this particular bit. For example, maybe you can prove that some quantity, such as the expected value of the function, tends to increase when you reveal a new bit. After n steps of doing this, you'll have the complete uniformly random vector x in your hand, but perhaps you'll be a little smarter. We follow the same approach, but with a continuous time process rather than a discrete coin flipping one. That is to say, every individual coin flip is itself simulated by a fluctuating continuous time process, and the eventual outcome of the coin flip is the final value of this process when it stops. To simulate a single bit, we let xt be a stochastic process such that the absolute value of xt is always equal to t. So xt is always equal to either plus t or minus t, and at every moment in time it has to decide whether to stay with its current sign or to make a jump of size 2t and flip over. Now, there are a lot of ways to decide how to make these jumps, but one way that makes a lot of sense is to make xt a martingale. Roughly speaking, a martingale is a random process where, if you know where you are right now, then in expectation, you aren't going anywhere. More formally, the conditional expectation of xt given what happened up to time s is equal to xs for t larger than s. This means that right at the start, the process is equally likely to hit either plus 1 or minus 1. However, as time goes by, the process fixates on which bit it is eventually going to hit. The closer it is to plus 1 near the end, the higher the chances that it will indeed hit 1 rather than minus 1. So the final process we use to generate our uniformly random vector, which we call bt, is just a collection of n independent copies of this martingale. Here are some samples of how it looks like in 3 dimensions. By the way, if you're wondering how to create such a martingale, here is one way. Start with a Brownian motion and keep track of its magnitude, noting down the times when it obtains a new maximum or minimum along the way. If you look only at times when the maximum increases or the minimum decreases, you get the process xt. So how do we use this process? After all, our function f is Boolean, but the bits aren't discrete anymore and may be assigned fractional values. Well, every Boolean function can be written as a multilinear polynomial. This is called its Fourier decomposition. Treating the Fourier decomposition as a real-valued polynomial, we can just plug in the stochastic process bt and obtain another martingale. This martingale too will jump. In fact, it will have a discontinuity whenever the underlying process bt has a discontinuity. If the martingale ft jumped because bt jumped in coordinate I, then we can calculate how large the jump was. The derivative in direction I tells us exactly what happens to the value of f when we flip the ith bit, and the jump is equal to 2t times the derivative. Analyzing the jumps of the martingale ft is important because of a quantity called the quadratic variation. This is a random process that is derived from the original process ft. The quadratic variation is very useful in stochastic analysis in general, but what is of importance to us in our case are the following two facts. First, the quadratic variation at time t is equal to the sum of squares of jumps of ft. And second, the expected quadratic variation is always equal to the variance at time t. Since b at time 1 is uniform on the hypercube, the variance of f of b1 is just equal to the variance of the Boolean function f. Thus, the variance of f is equal to the expected sum of squares of jumps of the process ft. And, after a little massaging and change of order of summation, using the fact that we know what the probability is to jump at any given time, this can actually be written as an integral. This equality gives us access to the large toolbox of real analysis, such as functional inequalities and differential equations. Using such tools, it is possible to bound the integral on the right-hand side, and thus give an upper bound on the variance, which is exactly what theorems of the type of KKL in Telegrand try to do. In fact, it is already possible to prove the KKL inequality from this equality alone, although this is certainly not the easiest way to do so. To prove Telegrand's conjecture, however, we need a bit more punch than just an expectation of an integral. Rather, our proof relies on inspecting the individual path which the random process takes. Since the derivative of function is non-zero only if it changes value, the sensitivity can be written as a sum of squares of derivatives, or in other words, it is a norm of the gradient. We can extend the gradient as a stochastic process too, giving us some function psi of t. Our goal then is to show that the expected value of psi at time 1 is large. As it turns out, the expectation of psi of t, conditioned on its past, is increasing in the time t. So in order to show this, we only need to show that the probability that psi t is large at any time smaller than 1 is also large. More formally, if we denote by tau alpha the first time that psi of t was larger than some number alpha, and set it to 1 if the event never happened at all, then the expected value of psi at time 1 is larger than the expected value of psi at time tau, which in turn is larger than alpha times the probability that tau is smaller than 1. All that's left to do is to pick alpha properly and show that this probability is large enough. Doing that entails studying how the individual paths of the influences vary in time. This is done using an inequality known as a level 2 inequality, which roughly states that the rate of growth of the sum of squares of influences cannot be large unless the sum of squares itself is large. Ideologically, this means that most of the movement of the process psi is performed at times that are 1 over log of the sum of squares of influences close to t equals 1. Until then, the gradient is practically 0. This type of phenomenon has been shown before, for example in work by Benjamini, Calais and Schramm, and by Keller and Kindler. Our result is a strengthening of previous work. We then show that with high probability, the quadratic variation is at least a constant factor of the variance, and also that a large portion of its gains are made when the gradient is large. This means that in the small time window that the gradient is large, it has to be really large, about 1 over the square root of this time window, which gives us exactly the required square root bound that we want. With any luck, I have convinced you that Boolean functions combined with stochastic methods are quite cool. It is my hope that there are many more inequalities and theorems waiting to be proved with this method, perhaps even by you.